As you might have already known, we are starting the lecture called Data Analysis and Machine Learning for Energy, Geoscience and Engineering. The lecture will be held by Michael Pyrcz, Associate Professor, Hildebrand Department of Petroleum and Geosystems Engineering, the University of Texas at Austin. And first of all, I'd like to thank you, Mr. Michael, for the SP Student Chapter support and sharing his knowledge in the field of data analysis and machine learning. Actually, despite this difficult situation in Ukraine, it's highly important for the students and young specialists to continue constant learning in order to rebuild and improve the oil and gas infrastructure in our state during and after the war started by Russia. So, dear Mr. Michael, I think that we can start right now, but the message before that, I want to give the message for the students. If you have some questions, don't hesitate to ask Professor after his lecture, or you can write down the questions in Google Meet chat and we will share it, okay? So, Mr. Michael, thank you very much. We can start right now.
All right, I appreciate it. Thank you so much for the introduction, for the opportunity to be here. I really do appreciate it. Let me go ahead and see if I can share my screen. I hope you can see my screen now.
We can see it now.
All right. Thank you very much. I appreciate it. And so what I want to do is, and excuse me, the title's a little different than what I put down, but what I want to do is I want to talk about how we can use machine learning and data analytics to support energy development for Ukrainian resources. Now, while I'm doing this, I hope you realize that what we're talking about here could be used for natural gas, resources, could be used for oil, and could even be used for mining. So if there's any interest in mining, these technologies, actually, I myself work in both the mining, oil and gas fields. I even work in groundwater. I even work in agriculture. So everything we're talking about here does have applicability in various different applications. Okay. Now, let me just ask, are you able to see my pointer on this app? You can see me moving around?
Yep, definitely.
All right, I'll use that to point. Thank you so much. So what's my motivation? Let me see, just by show of hands, are you guys able to put hands up on this? Who's been hearing about machine learning? Who's been hearing about data analytics? Are you guys having all this like digital revolution and people talking about that there? Anybody hearing about machine learning a lot these days? All right.
A little bit, I mean.
So it's happening, Anton. It's going everywhere in the world, right? We're hearing about machine learning. And what I want to do is I want to give you the opportunity to build new skills in digital transformation technologies like machine learning. I also want to demystify. I feel that there's too much kind of mystery about machine learning and data analytics, and I want to prevent you from being baffled. I want you to be a good engineer and be able to understand the technology, and I want to help with that. I want to share benefits and limitations so that you're able to be an informed consumer, so that when you're working with machine learning tools, you understand kind of what can be done, what cannot be done, what to expect from it. Also, I want to provide useful ideas and concepts and then invite you to try things out. So at the very end of this presentation, I'm going to leave you code and I'm going to follow up. I want to hear what happened with the code. I want you guys to try out some machine learning methods. I'll show you it. Don't worry. It'll be straightforward. So what I'm going to do, I'll first talk about myself very quickly. I promise, just like 3 slides of talking about myself. I shouldn't do that too much. And then I'll talk about the prerequisites, the fundamental concepts you need in data analytics and machine learning. We'll then cover a couple of examples of machine learning in the subsurface, oil and gas. And then we'll talk about best practice and new research. I'll talk about some of the research that's going on. Now, if you see this and you're interested and you want to participate, let me know, because I think there are opportunities for much more research in this field. And I'm always happy to look for collaborations across universities. Okay, about myself. I'm Michael Pyrcz. I'm a Ukrainian Canadian. It means that my father and his people immigrated to Canada quite a few years ago, but I grew up in the Ukrainian community, so I can say Slava Ukraini. And I really do hope for a fast end of the war and for free and independent and peaceful Ukraine. My heart goes out to Ukraine. And what I'm saying is that I am an educator, and I'm happy and looking for opportunities to do more to support with education. I have a lot of resources online, and I want to help out. So please, let's follow up. I want to keep going with this. I have practical experience. I'm not the regular professor. I spent 17 years in industry doing the things that I talk about. I worked in Chevron's energy technology company. I was one of the experts in data analytics and geostatistics. I'm available. If you have questions, drop me an email. Now, since I've met with you, we're now family. Go ahead and send me an email. If you have any questions, please put the name of your school in the subject line, and I'll know to answer the email. I get 100, 200 emails a day, but if I see the name of the school, I'll be like, hey, I know these guys. I got to answer that email. Background. I left industry to give back. I really do love to teach. And so while I'm a University of Texas at Austin professor, I still teach in industry and other education in other institutions as much as possible. I'm very active in outreach. I have anybody on Twitter? Is Twitter something people do in Ukraine?
Yes, there are some.
Yeah, we have Twitter, but not so often. Sitting there.
All right. Is anybody following me? I'm the Geostats guy on Twitter. You don't have to.
Not so.
No pressure. But I'll tell you what, on Twitter, what I do is I share educational content. I share my workflows. So if you are interested, I have also all of my lectures from university on YouTube. So if you go to YouTube, Geostats Guy Lectures, you have all of my courses. Anybody here going on GitHub? Who's on GitHub? Anybody coding, putting on GitHub, downloading code from GitHub? If you go to GitHub, you can find I have hundreds and hundreds of well-documented workflows. So all of my educational content from the University of Texas at Austin is available to anyone in the world to support them. And I have a bunch of PhD students. I do research. Okay, that's it. I don't want to talk any more about myself. I'm sorry, that was like 3 slides of it. Let's talk about prerequisites. Anybody here working with big data? Anybody have big data experience? Big data, if you look up big data online, you'll get this definition. The criteria for big data are the V's: volume, velocity, variety, variability, and veracity. Let me explain a couple of these. Volume, many data samples, difficult to deal with. Now let me ask you this. In oil and gas, do we have big data? Do we have many samples to work with and difficult to visualize? Well, of course we do. When we have seismic acquisition in the US, United States, in the Gulf of Mexico, the data transmission rates actually rival that of Google or JPL or any of these other big data companies. We have big data for volume. What about velocity? We have a high rate of collection of data. In fact, those who work in the industry will know that we're always challenged to go through our workflows and to be able to be able to process the data in time to keep up with the bit. We're always trying to keep up with the drilling operation. So we have velocity too. Let me do one more. Veracity. In the subsurface, do we have any certain, no uncertainty data? And I think the answer is we really don't. All of our data is uncertain. If you measure a well log, well, there's calibration at the well log, there's decisions about the rock physics, the rock and the fluid system. If you have seismic, it's at very low resolution, but has good coverage. All of our data has uncertainty issues. The subsurface has been big data long before tech. Google, Amazon, anyone learned about big data. So what do I tell you? If you work in oil and gas, you're the original data scientist. You work with big data. What about topics like statistics and geostatistics and data analytics? Well, statistics, oh boy, that's collecting, organizing, interpreting data, as well as drawing conclusions. to support decision making. Okay, that if I drew a Venn diagram, it would look like that. Statistics. Then we have geostatistics, us in oil and gas. We have our own branch of statistics that deals with the spatial, subsurface, reservoir, geologic context, the spatial relationships like varigrams, the volume support, the scale of all of our data, and the uncertainty in our data. Okay, so if you take geostatistics, it's a branch of statistics. Now, what's very interesting, if you look at a definition of data analytics, it's analysis of data to support decision making, which is very interesting to me because if I look at it and I go back, statistics, data analytics, they're really the same thing. In fact, if you do statistics in your job, please update your CV. Big data analytics is the process of working with big data to discover patterns, to be able to support decision making. Okay, that's statistics or data analytics on big data. And spatial big data analytics, that's when you're working with the spatial context, like the subsurface. Data analytics is the use of statistics and visualization. Now, what is machine learning? We're going through prerequisites here. I'm almost done with them, but what is machine learning? It's the study of algorithms and mathematical models that computer systems use to progressively improve their performance on a task. Okay, so it's a mathematical model, and it's more than one. It's a group or toolkit of mathematical models. They are learning and improving their performance. So they're learning tools, and the machine learning algorithms build a mathematical model of sample data known as training data. Okay, so mathematical models that are learning from training data, and in order to make predictions or decisions without being explicitly programmed to perform the task. Okay, so they're general. You can have a machine that is able to work on a drilling problem, prediction of, say, rate of penetration, but you can use the same machine, train it with different data, and it can predict the porosity at an unknown location. So you can use it for different tasks. Now, the important thing is many people, when they read the definition of machine learning, they don't go to the end of the article. And there you'll hear where it is infeasible to develop an algorithm of specific instructions for performing the task. What does that mean? It means if you're an engineer and you know the engineering physics to solve the problem, use that. Don't use machine learning. No, not unless you need very fast predictions, not unless you don't fully understand the physics. There must be a justification. But if you know the physics and you can do that, it's better to do that. Okay, what is a machine learning model? You can hear about all different types of machine learning models. You got convolutional neural nets, you got artificial neural nets, you got random forest, you got support vector machines. There's so many different types. But what they all are is this. This is what it is. It's just a function. You have a model that takes the predictor features. Those are the input variables to the model. So you could have porosity, permeability, saturation, so forth, rock type, lithology. And then you have the response. The response is the output. The response feature could be something like production rate, cumulative production over 2 years, or maybe you're trying to predict the facies at an unknown location. Whatever the model's trained for, you have inputs, you have outputs. This is what machine learning is. Now, there's two purposes for machine learning. There's two reasons we do it: inferential and prediction. Inferential goes like this. We're trying to understand the relationship between all of the inputs. We want to understand the population, the system, the reservoir. We want to understand if there's positive or negative relationships between the features. Is there specific sweet spots in the relationship where you have a good combination of inputs to get a good result? Recall, inferential statistics would be the problem for which you have a coin, and you say, given I had 3 heads and 7 tails flipping the coin, what is the probability the coin is fair? In other words, given the sample, what is going on with the population the sample came from? That's inferential, learning the population. Prediction goes after inference. After we understand the population, we can now make predictions with our model. And so when we do predictions in machine learning, we're taking inputs and we're trying to find the output, the most accurate output possible. Now we show an F hat because the function is an approximation of the natural setting, and the output is of course going to be an estimate of the output. Now recall, what is predictive statistics? It's the problem of, I have a fair coin. I inferred the population. The coin is fair. Now what is the probability of 7 heads or 7 tails and 3 heads in the next 10 coin tosses? In other words, given an assumption about the population, predict the outcome in the next sample. Okay, so that's prediction. Now, when we build our machine learning models, we got 2 different types of models we can build. We got parametric models. A parametric model makes assumptions about the functional form or shape of the relationship. When we do that, we gain simplicity, the advantage of having only a couple of parameters to estimate. Here's an example right here. We have depth in Z, this is meters, and we have porosity standardized, it's normally transformed or something. Okay, so we got our data right here. The pink circles are the data, and we got our model. If it's a linear regression model, it's a line. We're going to fit a line. And how many parameters do we have? We have a slope, and we have an intercept parameter. That's all we have to work with. Okay, so we have very few parameters. It's easy to estimate, but we can see that the parametric model can be wrong. You see the data? It does that. It's not linear, and so it's not a very good model. So we got to be careful of parametric models. A non-parametric model for machine learning makes no assumption about the functional form or shape. It's more flexible to fit a variety of shapes. Okay, so here's an example from decision trees. And so the decision tree model is able to learn the shape of the relationship. It's not stuck with a linear model. The problem is that when we have non-parametric models, they in fact are parameter rich. They have many parameters. This decision tree model, every one of these transitions is a parameter. Every one of these values here is a parameter. So it's 1, 2, 3, 4, 5, 6, about 20 or more parameters. So that's quite a few parameters with very few data. And so that can be very dangerous. You need more data to estimate a non-parametric model. Okay, so I'm going to show you in one slide, how do you do machine learning model fitting? How do you build a machine learning model? It's very, very simple. Let me show it to you. It goes like this. You take your data. So once again, Z elevation, and we have permeability this time. We have the data. You see all my data. What you're going to do is you're going to take a certain subset of the data and you assign it as testing data. You see the circles? Boom, boom, right here. All of these circles right here. You take them and you put them aside. You hide them. You don't look at them. Then what you do is you take this remaining data, the training data, you go ahead and you fit a model. Do you see my linear regression model right here? It's just a linear regression model. I fit it to get the very best fit to minimize error with the training data. Then I take a higher order polynomial, a 3rd order, a 5th order, a 7th order model. The models are getting more and more complicated as I go down. Then what I do is, remember that data, that testing data? I go ahead and I grab that testing data and I bring it back and I check the model performance with the testing data. Here's the data right here. I did okay. That's the error right there. Here's the model right here. I did very good. This is a very good model. It fits the testing data very well. And look at this model right here. Can we all agree that model is terrible? It's not a good model. At the testing data, I do very poorly. And this model right here, awful. This is a very bad model right here. Okay, so what we're going to do is we'll look at the error in testing with the withheld data, and we'll pick the model that has the best performance with the withheld data. What are we doing? If we were to pick the model that best fits the training data, which model would we pick? we would always pick the most complicated model because it's most flexible to fit the data. But that model would be overfit. It would be a very poor predictor away from the data. So we're trying to prevent overfit. Now, I've used some terms, so I got to define them now. The first term is model parameter. If I build a third order polynomial model, so I have my polynomial model right here, B3, B2, B1, and the constant term, also known as B naught. Those are coefficients, but they are the parameters of the model. If I change them, the model moves around. It moves up and down. I change the curvature, and that will cause me to be able to best fit the data. So training model parameters with the training data. That's what we were doing. The model hyperparameters are totally different. Model hyperparameters constrain the model complexity. The choice of polynomial order, third, second, first order linear model, that is a model hyperparameter. Okay, so this is the hyperparameters right here. And what we do is we use the testing data to tune the hyperparameter to get the right level of complexity for our problem. Okay, model parameters, hyperparameters, training, and testing, that's how we build our models. Now, what are we doing? Why do we do all of that? Well, at the end of the day, it all comes down to the model variance bias trade-off. If we're trying to look at the performance of a machine learning model with the withheld data, in other words, how does our model perform when we use it for new predictions, not at the training data? We calculate that as the expected, as in statistical expectation, test mean squared error. Now, if you look at it, the calculation's this. This is the truth values for the response feature. These are the predictions from our model at not locations not used to train the model. If we take this expected squared value, that's our expected test mean squared error. Now, what's really cool is you can take this expectation quadratic, expand it, simplify it, and you get three additive components. These are the three components of model error in real world use. Okay, the first one, model variance. The model variance is error due to sensitivity to the data set. In other words, if you increase the model complexity, here's a simple model, here's a complicated model, what'll happen is the error will go up. Because what's happening is that as you get a more complicated model, the model variance causes the model to be more sensitive to the data. Let's think about that. If you have a linear regression model, if you change the training data, your linear model will move around a little bit, not too bad. If you have a ninth order polynomial, you know those really high order polynomial models, if you change the data just a little bit, that model will whip around like a whip. It will be very unstable. That, my friends, is model variance. More complicated models are more sensitive to the data, and that's a source of error. They're unstable. Model bias is error due to using an approximative model. Now let's think about that. A linear regression model is very simple. And so that model is unable to fit complicated forms in the data. In other words, a simple model like linear regression will have high model bias, but a more complicated model like a ninth order polynomial will have low model bias. Now they're additive, so we can add them together, but there's one more term we got to talk about, irreducible error. Irreducible error is due to missing variables or features, missing data, limited sampling. Now let me ask you this, in the subsurface, do we ever have enough data? What proportion of the subsurface do we sample directly through drilling? I ask my students this all the time, and I'll tell you what we know, and that is 1 trillionth is the typical number. Think about that. Volumetrically, we sample about 1 trillionth of the reservoir. Do we have enough data? No, we never have enough data. That's irreducible error. Okay, and irreducible error does not depend on the model complexity. It depends on the data. So it's constant. If you take model bias, if you take model variance and irreducible error and you add them together, you get the expected test mean squared error. Now, what does that look like? The expected test mean squared error, if you add them together, will do this. It'll, at a simple model, it will be high. It will come down. You get less and less error. And then as the model gets more complicated, it'll go back up. That's because of this model variance. So what do we know? If we're engineers and we see error and we see a function like that, we see a minimization problem. That is what model tuning is. We're trying to find the model complexity so that we minimize the error. Now, we have to do it with withheld testing data, because if we did this with the training data used to build the model, to train the model parameters, the training error will keep going down and down and down. Eventually, you have a complicated enough model, you can perfectly fit the data. But that's not the best model. That's not going to perform well at withheld or new prediction problems. You need a model like this, which is more of a compromise. It will perform better with new predictions. All right, that's it. That's all the prerequisites that I want to share. I hope that that was helpful. Big data. We talked about data analytics and statistics being the same thing. We talked about how we build machine learning models, what types of machine learning models we have, parametric, non-parametric, and model tuning training related to the variance and bias trade-off. Okay, I hope that was helpful. Now let's talk about subsurface data analytics and machine learning. I'm going to get a little bit philosophical. Has anybody here ever been welcomed to the fourth paradigm of data-driven science? Anybody ever had anybody say, welcome? And I'll tell you what, if not, let me be the first to welcome you to the fourth paradigm of data-driven science. Now, what are the other paradigms? First paradigm of scientific discovery was empirical experiments. Well, the Egyptians were doing that. We can dig up and they were, oh man, I'm glad I'm not part of an Egyptian medical experiment. But they were doing experiments. The second paradigm, so we've been doing that forever. Second paradigm, theoretical science. Laws of classical mechanics, electrodynamics, whatever. These are all of the fundamental physical laws. We start to learn those back during the 1600s and so forth. The third paradigm is computational science. The world is complicated. It's not homogeneous. It's heterogeneous. The geometries are complicated. The systems are coupled. You can't solve problems with fundamental analytical relationships in theoretical science. You have to do computational science. And so continuum mechanics of heterogeneous systems, computational fluid dynamics, these are examples of third paradigm activities. Flow simulation for predicting, forecasting, production, that's third paradigm. The fourth paradigm is when we go to the data and when we have sufficient data and we detect patterns, anomalies in our big data. We use artificial intelligence, machine learning methodologies. That's the fourth paradigm. Now, if your group, if your school, a company you work at are facing the digital transformation, you're not alone. In fact, Deloitte did a study back in 2019. They looked at the United States and they looked at a bunch of different sectors of our economy and they ranked them based on maturity, readiness for digital technologies, machine learning, data analytics. And what they found was TMT, tech, media, and telecom. Okay, they're in the front. They have the most readiness, 34% organizations, high maturity. But when they looked at energy, they found we were in the middle of the pack. In fact, we were much better than government, life sciences, health, and so forth. We actually are moving in this direction for sure. I visit a lot of energy companies all over the world, and every one of them is working on digital technologies. What is my viewpoint? What do I think about it? I'm an engineer. And what I would say is there's opportunities to do more with digital, with machine learning and data analytics. Yes. Opportunities to teach it. In my university, University of Texas at Austin, I teach data analytics and machine learning. I supervise like 12, 14 PhD students in it. I teach machine learning courses. We are ensuring that our students understand the digital technologies in addition to engineering. Geoscience and engineering knowledge and expertise remains core to everything we do. I go to many organizations, they got a data scientist, and the data scientist really doesn't know much about oil and gas. And I'll tell you what, I don't think that's the best. They have to work together with the engineers, and I think it's even better for the engineers to know something about data science. I think that can be very helpful. Working in the fourth paradigm, what do I say about it? When we developed the third paradigm of computational methodologies to discover things about the world, well, we were using the second paradigm, theoretical science, to make that computer program. We were using first paradigm empirical experiments to calibrate that program. In fact, we use both. What do I say? Even though we have fourth paradigm for data-driven science, we do not replace the old paradigms. We still remember all of our engineering. Okay, data preparation and working with data remains essential. Every project I work on, 80% or 90% of our time is getting the data ready with engineering and geoscience interpretation and processing in order to build our machine learning models. So still, most of the work is going to be the engineering and understanding the data. Remember, garbage in, garbage out. If we don't do a good job with our data, our machine learning models are useless. They will not do very well at all. Now, the subsurface is very different than many applications. Let me ask, does anybody here use Google driving directions? Anybody use that? Google driving directions? Or how about, does anybody use Spotify?
Yes.
You use it, okay, good. Google driving directions, thank you very much. Or Spotify. Let me show you something. Well, first of all, let me just say this. These applications of machine learning are totally different than our application in the subsurface. We have sparse, uncertain data, complicated, heterogeneous, open earth systems. We don't fully understand them. We're doing our best. Okay, does Google driving directions have sparse data? No. They know what everybody else using the app is doing. They see everybody driving. They have lots of data. High degree of necessary geoscience, engineering, interpretation, and physics. Is there any physics to driving directions? No, it's just data driven. It's just the data. How about expensive, high value decisions that must be supported? What is the cost of Google driving directions taking you the wrong direction? What's the cost of drilling a well in the wrong location? In the Gulf of Mexico, about 5 years ago, it was costing us $150 million to drill one well. Our exploration budgets were often $1 billion. How much does it cost to get that wrong? $1 billion. Okay? Now let me compare that to Spotify. I'm a Canadian and I listen to a lot of Canadian music, but there's a band I don't like very much. Is it popular in Ukraine? It's called Nickelback. Have you ever heard of Nickelback?
No, you don't
No,
hear.
okay, good. You know what? That is fortunate for you, because I'll tell you what, they're terrible. Nobody likes Nickelback anymore. But every once in a while, Nickelback plays on my Spotify. When it comes on, I just go, okay, it's Nickelback. I fast forward. It is the application getting it totally wrong. You see what I'm saying? But there's no cost to getting it wrong. In our field, $1 billion, $150 million per well to get it wrong. We need to be critical users of the technology. In fact, companies I go to refuse to use machine learning unless they can understand the machine, because it's so expensive, the decisions. Okay, so let's just remember, don't jump to complexity. In fact, if you look at the expected mean squared error, you're going to find that most of the time, the most complicated model due to model variance is not the best model. We had a hackathon. We hosted a hackathon in our school. The winning team used linear regression. They used linear regression and they won $5,000 and the entire hackathon. Don't jump to the most complicated model. Now, here's an example right here of machine learning that's very interesting. Anybody ever heard of convolutional neural nets? It's a form of machine learning that's able to look at images and see things. Here's an example of convolutional neural nets right here. So it turned out that Ribeiro and al. Back in 2016 took pictures of dogs and wolves. I hope there's people here who are dog people. And when they looked at those, they trained a machine, and the machine was able to predict, is this a dog or is this a wolf? Okay, now, any dog people out there, can you tell me, is this a wolf? Does this look like a wolf?
Probably it's a dog.
You nailed it. That's a dog. It's a husky. And the huskies, you know, so when it came back saying 100%, 90% wolf. And they looked at the application and they said, what's going on? And so they went into it and they said, tell us the pixels of the image that give it a high probability of wolf. And when they did that, these are the pixels that showed up. What did the machine learn to do? Did the machine learn to detect wolves and dogs? The machine had learned to detect whether or not the dog or wolf is standing in snow. The machine was detecting snow. Okay, now you can see that the problem with machine learning methods, if they're very complicated, we may not understand what the machine is learning, and it can get it totally wrong. When we work with complicated machine learning, while the interpretability may be low, application may become routine and trusted, and the machine is trusted, it becomes an unquestioned authority that can totally get it wrong. Now, let me just comment on data scientists, because in our school, we're hearing a lot of people say, we want to see more data science. Okay, now what we need to remember is that data science is going to be statistics, coding, workflow construction, and domain expertise. Now, what I say as an engineer is that this is what we should be doing. We should be taking our good engineering knowledge and building that up even better. That's the main thing, is our engineering knowledge. And then we take our knowledge about statistics, which is geostatistics. That's what we do in oil and gas. We build on that, and we use that, integrate that. Next, we should grow our capability coding, scripting. I don't care, Python, C++, whatever it is that you need to build your workflows. We build workflows. That's what I think we can do. I think engineers can become very good data scientists by building on our engineering knowledge. What I'm going to do now is I just want to show, I'm going to skip through a little bit of this, to right here. I want to just show you, I have some example data sets where I do some machine learning model training. And I want to just show you the data set right here. Then I'm going to give you a link at the end of the lecture that you can use to go and try this out. I'll tell you what, I'll send it to Anton at the very end. I'll send an email with a link to this workflow and you can try it out. I have put together a workflow with a variety of machines. Here's the prediction problem. You have porosity that's been standardized. So it has a mean of 0, variance of 1. Not a big deal. That's okay. You have brittleness. Now this is unconventional. So shale in the United States. So we're interested in the frackability of the rock, the brittleness of the rock. So we have a brittleness index that we have standardized. Then we have our data, and the color, the Y coordinate, is the production in MCFPDs. Okay, so this is going to be the production of gas per day. And you can see the production shown right there. And so their dots are right here are the training data. Here's a linear regression model that I fit. Now, when we do linear regression, very simple. How do you know it's linear regression in 2D? It's going to be a flat plane. It's going to be a plane because it's linear regression. It can only model a plane. Okay, now what we do next is we try out k-nearest neighbors. K-nearest neighbors is a form of machine learning that's analogous to mapping. It's a geoscientist would use it to build a map. Even an engineer would build a map with it. And so k-nearest neighbors takes on the problem of using the nearest number of data to calculate an average and to build a map. Okay, it's like a convolution method. You can try that out too. And you can change the k hyperparameter and change the complexity of the model. Next, we have decision tree. A decision tree does a hierarchical binary segmentation of the feature space, porosity, brittleness, and it breaks it up to regions, and it uses the average of the training data in the regions. Okay, here's an example. How do you know it's a decision tree? You can see the discrete regions. Very good. So you can try out decision trees with my code. Next, you have random forest. Random forest is a tree-based ensemble method. It's going to take a whole bunch of different trees, train them, and take the average of the trees. By doing that, you see a decision tree creates a discrete model with constant estimate values in each region. A random forest will create more of a continuous model, and it will greatly reduce model variance. It can give you a much more stable solution. Okay, you can try out random forest in the code that I will provide. Now, every one of these topics, I could come back and we could do a lecture on random forest. We could do a lecture on decision trees. We could do specific lectures. I have many lectures. You can go to my YouTube channel and you'll see many, many lectures on these topics. Finally, gradient boosting. Gradient boosting is really cool. Anybody here ever done gradient descent optimization? Gradient boosting is a form of gradient descent optimization, which we engineers do in optimization. It even has stochastic gradient descent. Okay, so we can use that in order to do additive models to get a very good prediction model. Okay, so those, I will provide the link to a Jupyter notebook, well documented for you all to try out these different machines. Let me just make a couple of comments about best practice, and then I'll show a couple of research ideas, and I'll be done, and I'll leave 10 minutes for questions. Fit for purpose modeling. Anybody ever seen this before? Good, cheap, and fast. This is commonly used as a kind of a pseudo Venn diagram to describe how we build projects. You can't have good, cheap, and fast. You have to pick. When you do machine learning, remember that. You have to make a choice. If you want it good and fast, it's going to be expensive. If you want it good and cheap, it's going to be slow. And you can do fast and cheap, but that's just low quality. Don't do that. Okay. The other thing is modeling for discomfort. Anybody ever seen the work of Mark Bentley on geomodeling for oil and gas? Very good paper. Very good paper. He talks about this idea that we should model so that we test what's going on in the subsurface. Models become tools for verifications of decisions already partially or fully made. This is called modeling for comfort. Mark Bentley said, do not do that. So when we do machine learning, let's have the attitude of modeling for discomfort. Build models so that we're testing the uncertainty space. Build models so we're being scientifically critical. Okay, those are a couple of comments. The other thing I should mention is that my brother, I have a twin brother in Canada, and he's a machinist, and he's a very good machinist. He can make, like, if something breaks in his house, he takes a block of aluminum and makes it. He has like all of those like multiple axis CNCs. He does all that stuff. The machinist knows how to machine very well. They're experts. My grandfather was a machinist. His tools have his hand carved into the handle because he was machining for 4 decades, 5 decades. For 40 or 50 years, he was a machinist. He knew how every tool worked very, very well. What I say is if we're going to do machine learning, we should be inspired by the machinist. We should know the tools that we work with, as well as a tradesperson knows the hammer and their chisel and their different tools. I also have many resources online. As I mentioned before, I have all of my lectures, multiple, like 160 lectures now on my YouTube channel. I have hundreds and hundreds. It's not 60, it's like 200 well-documented workflows. I have all of those available, and I have information about how to get started. Coding. If you don't code now, please let me just encourage you to code. Okay, here it is. I promised all of those example models. I have a link right here. Check out that link. I can send it to you. I can share the slide deck with you. You can go to the GitHub, download it, well documented. You can try out all of these machines with a little bit of information. I can come back and talk about them. Okay, let me go ahead. I want to show you just a couple of research ideas. Spatial anomalies. When we drill data, everybody see this is Y, this is X, This is a porosity over the wells, average over wells data set for a pretty good field. We got 1, 2, 3, we got about 200 wells here, or maybe 300. Well, it turns out that if you drill a well, you see the porosity is pretty high there. Is that porosity unusually high or not? We used machine learning data analytics to build a method for anomaly detection. It went through all of the pairwise connections between data, and it found these are anomalous. They are unusual changes. And so we can build maps right here with a probability that we can then use to detect where are weird things or strange things happening in our data. I want to show you one more thing here. We've been working with deep learning to do seismic downscaling. The problem is this is a two-dimensional view of our reservoir. And if you look at it, this is what you often see in seismic. You just see from acoustic impedance, inverted seismic, you see, okay, we have a sand body. But you don't need that. What you really need is something like this to do flow simulation. Seismic cannot support flow simulation. We used deep learning to do downscaling from this to this right here, or from this to this. So basically, we're able to go ahead and say, given this seismic information, give us a realization of what the reservoir could look like. Now you can flow simulate that. We've been working on seismic downscaling for flow simulation support. Now, we've also been working in all different types of reservoir model construction. This is a fluvial meander channel type of reservoir confined in a valley from seismic mapping. And we're able now to build models like this. This is much better than any of the geostatistical models we were building previously. So I'm excited. This is coming from deep learning, from machine learning. I think it's going to change how we build our models. Okay, one more thing. Just one more thing and I'm done. This is a high resolution model taken from a scan, a CT scan of a rock sample that was about 2 centimeters by 2 centimeters, a very tiny piece of rock. What we did is we then ran a flow simulation based on lattice Boltzmann to basically be able to calculate the high resolution velocity field. Next, what we did was we were then able to go ahead and we were able to calculate the predicted from machine learning, deep learning model of velocity at high resolution. When we compared them, the relative error was actually most of the time about 10-20%. Well, guess what? If you have high resolution velocity fields that you can calculate in like a thousandth of a second, you can do very good flow scale upscaling from pore scale to reservoir scale. We think that this is a big step towards bridging the gap between rock, grain structure to flow simulation, or even detailed fracture models to flow simulation. These are all based on deep learning models. Okay, what are we doing? What are the concluding remarks? Data analytics and machine learning provides new tools, the fourth paradigm of scientific discovery, data-driven discovery. Efficiency and automation, engineers and geoscientists doing more engineering and more geoscience. Detecting anomalies, focus on what matters. Find the important things in your data. Finding new patterns, pose new scientific questions. Assisted interpretation, working with big data. And new improved models, better integration of expert knowledge. We see a lot of opportunity through machine learning, and that's why we teach it so much at the University of Texas at Austin. All right, concluding remarks. Engineering expertise remains core to everything we do. We're not replaced by computer scientists. We augment our abilities with new digital capabilities. Before, those with the best data used to win. Now it's those with the best data and use the data best. Those are the ones who win when it comes to projects and companies. All right, I want to acknowledge this talk was actually part of an AAPG Distinguished Lecture talk, and I appreciate their support.